Here's another question. So determine the capacitance that can be applied to a Teflon filled parallel plate capacitor having a plate area of 185 centimeters squared and insulation thickness of 0.0830 millimeters. Also, in part B, determine the maximum voltage that can be applied to a Teflon filled parallel plate capacitor having a plate area of 185 centimeters squared and insulation thickness of 0.0830 millimeters. All right, so the first thing we want to do is write down our information. So in part A, okay, we are given that the area of the plates is equal to 185 centimeters squared. And we also know that we have an insulation thickness, which I'll call D, and that's equal to 0.0830 millimeters. And the material that we're looking at is Teflon. So I'm gonna write down that as well. The material is Teflon. Now, this is really important when talking about capacitances because the different dielectric materials have different dielectric constants. So for instance, the dielectric constant for Teflon, so kappa Teflon, is equal to 2.1. That is the dielectric constant for Teflon. And we also know that the dielectric strength, if you remember that table that we had in the PowerPoint presentation, it had a list of what we call the dielectric constants, which is this kappa, and also the dielectric field strength, which is the electric field, the maximum electric field. So that maximum electric field is equal to 60 times 10 to the 6 volts per meter for Teflon, or you can say 60 times 10 to the 6 newtons per coulomb. Depends on what type of units that we're dealing with. And I'm going to guess that we're going to be dealing with this over here, okay, based off of what our capacitance equation holds. So for part A, let me just erase this, but for part A, we want to find the capacitance. What is that capacitance? Well, we know that the definition for capacitance, C, is equal to, when we have dielectric, we include this dielectric constant times epsilon naught times the area of the plates divided by the distance between them. And so here we have the value 2.1, epsilon naught, which is 8.85 times 10 to the negative 12 coulombs squared over newtons times meters squared, times the area of the plates, which is 185 centimeters squared. So let's just say 185 times 10 to the negative 4. Let's convert that to meters squared, divided by the separation between the plates, which is 0.00, or not 00, but 0.0830. And I'm gonna just say times 10 to the negative 3 meters, just to go on ahead and convert that. So we have everything in MKS units, meters, kilograms, and seconds. Okay, that's how we want those units to be broken up. So once we do this, we calculate the capacitance. The capacitance comes out to be 4.14 times 10 to the negative 9, okay? Now, we know we're dealing with capacitance, so our units are gonna be in farads here, but how did we get those farads? You notice that I'm very interested in the units. So let's go over here to the side and let's look at some units. So for the units, we know that we have, let's see, so we have this, okay, this is a Coulomb squared divided by a Newton times a meter squared. Then we have meters squared, and that's divided by meters on this side. So our meters squared and meters squared are going to cancel, and we're left with Coulomb squared divided by Newtons times meters. Well, I know that this Coulomb squared is going to stay, but then this Newton times a meter, that is equal to a joule, if you recall from last semester. And so now we have a Coulomb per joule times a Coulomb, and I'm just going to say that is a Coulomb divided by a joule per Coulomb. And this is a Coulomb, a joule per Coulomb, remember, is a volt, okay? And a Coulomb per volt is a farad. So that's where that farad comes from. Now we see that this is to the order of 10 to the negative 9. So we're going to say that that capacitance is just equal to 4.14. 10 to the negative 9 is nanofarads. So that is our capacitance, okay? Once again, 1 nanofarad is equal to 10 to the negative 9 farads. So that's how we got this. Now for part B. Let's do part B. So for part B, they want us to find the maximum voltage. Okay, so what is delta V max? That's what they're asking us. What does that equal? Well, I know since I'm dealing with some maximum voltage, I have to be talking about the electric field strength, or that, that dielectric strength. That's that maximum electric field that we talked about in that chart. So I know that I'm given that maximum electric field up here, and I know that delta V max can be represented in terms of the electric field. In this case, it's that maximum field, that dielectric strength, times the separation distance between the plates. So this equals to 60 times 10 to the 6 newtons per Coulomb, times that separation distance, which is 0.0830 times 10 to the negative 3 meters. This gives us a maximum potential difference of 4,980 volts, which is equal to 4.98. I'm going to convert this to kilovolts, okay? This is our maximum potential difference.